Look at the size of this nuclear containment dome under construction on the coastline. A standard commercial building wall is about 20 centimeters thick. A nuclear shield wall is 3 meters thick, packed with an extremely dense matrix of reinforcing steel. At 3 meters thick, this structure crosses the threshold into what engineers term mass concrete. At this scale, the internal thermodynamic forces generated by the curing process become as lethal to the structure as external physical loads. To regulate construction under these extreme conditions, the Architectural Institute of Japan mandates a dedicated specification standard, JAS 5N. Designing nuclear concrete under JAS 5N requires engineers to simultaneously solve 5 intersecting constraints. Those constraints are seismic safety, thermal cracking control, constructability, radiation shielding, and long-term degradation mitigation. Deliberate, failing to balance even one of these 5 vectors will cause the concrete member to fracture and fail from within before the facility is ever operational. This overhead view captures the geometric footprint of the reactor foundation mat before a single drop of concrete is poured. The first pillar is structural safety. The concrete must maintain severe accident mitigation functions against the maximum design base earthquake, known in Japan as the SS. Resisting the SS requires evaluating complex seismic response analysis, internal stress loads, and the exact ground bearing pressure holding the massive structure up. It must also satisfy the fourth pillar, shielding and temperatures. This concrete acts as both physical confinement and a radiation shield. Gamma-ray shielding walls are evaluated conservatively, assuming they will operate continuously at long-term accident temperatures reaching 78 degrees Celsius. Sustaining 78 degrees Celsius for extended periods alters the physical properties of the concrete, inducing entirely new internal stresses. The combination of extreme seismic resistance and thermal radiation shielding mathematically dictates the massive geometric scale and heavy initial steel density of the foundation. When you look inside that foundation, you find a highly congested spiderweb of reinforcing steel. The requirement to withstand that design basis earthquake is the primary driver forcing this heavy reinforcement. The internal congestion is compounded by the thick steel plates, piping sleeves, and containment liners required for plant operations. There is an assumption that a 3-meter thick wall is easy to pour, simply because the volume is large. The physical reality is the exact opposite. When viscous concrete is forced through these dense metal zones, it struggles to flow smoothly, leading to filling defects and honeycombing. These empty voids act as structural weak points, frequently causing localized cracking directly around the heavy embedments and liners. To prevent this, the exact rebar detailing, the precise pour sequence, and the mixture's physical consolidability must be mathematically modeled before construction begins. Maximizing the cross-sectional seismic strength inadvertently creates a severe physical barrier to actually building the structure. The AIJ guidelines mandate strict thermal control protocols for walls over 80 centimeters thick and slabs over 100 centimeters. This diagram compares that 80 centimeter threshold against the actual 3-meter depth of a nuclear basemat. As the massive volume of concrete cures, the chemical heat of hydration creates a rapid temperature rise in the core, forcing the material to expand. Simultaneously, the surface layers cool faster. This cooler surface resists the core's expansion, generating massive tensile stress. This immense temperature differential pulls the material apart, resulting in catastrophic thermal cracking from the inside out. Engineers combat this chemically by suppressing the unit cement content and utilizing specific moderate or low heat cement blends. But the sheer scale of the heat requires extreme mechanical intervention, aggressive pre-cooling of the materials before the pour even begins. On Japanese construction sites, contractors cycle chilled water, integrate raw ice flakes, and inject liquid nitrogen directly into the concrete slurry. The strict target placing temperature required for a basemat is exactly 20 degrees Celsius. At a thickness of 3 meters, calculating cross-sectional yield strength is useless if the internal thermodynamic stress is left unmanaged. The final variable is time, strictly governed by the Nuclear Regulation Authority's high aging evaluation criteria. Over decades, coastal and underground structures face continuous external attacks from salt penetration and groundwater chemical erosion. Internally, there is the threat of alkali-silica reaction, or ASR, a slow chemical process that causes severe expansion within the aggregate. Areas exposed to the continuous 78-degree temperatures required for gamma shielding inherently accelerate these chemical degradation processes. Making a structure 3 meters thick does not provide passive immunity to environmental aging. It requires active chemical mitigation built into the initial design. Designing a 3-meter-thick nuclear concrete member is an exercise in extreme, calculated compromise. Optimizing solely for maximum seismic strength packs the volume with steel, which immediately compounds the constructability and thermodynamic vulnerabilities. JAS 5N compliance demands balancing structural safety, thermal control, constructability, shielding, and degradation mitigation. Under Japanese nuclear engineering standards, satisfying only 4 out of these 5 parameters is categorized as a complete design failure. This matrix of constraints is solved for the horizontal base mat, but the equations change entirely when that 3-meter slab is rotated 90 degrees to become a vertical shear wall.